so the idea is that we want to define these type of programs. This is not like that. So let's say I have a string, and I'm just gonna put it and then loop again. I'm just gonna keep printing that string over and over again. And we want to be able to have concurrent actions. And so the result should be some kind of interleaving of the loops. But of course, if you write IO main to loop cat, loop fish, well, what's going to happen is I'm not showing the, can I do it in here maybe? Surely. Whoop. Oof.
Okay, if you 1 second, we can't hear audio apparently. But I'm sharing the virtual camera, so I don't.
Yeah, so just printing cats a lot of times and then never reaching fish because these things are not actually concurrent, they're running one after the other.
1 second.
Uh,
Sorry, there's no audio apparently, and I can't figure out how to get audio from OBS into Zoom.
In Zoom, you can just select your source, right?
Yes, but there is no OBS source for the microphone.
Then you just use the normal source.
Pardon?
Maybe we can test it, set up another tape. Just like
Just select
Guillaume connected.
Yeah, that's fine. I think it's this one, and then try this. Now, could you try speaking?
Yeah, I can speak.
Okay, apparently good. Good. Sorry about that.
No worries. Okay, so we have these kind of things, and what we would like to do here is have a different semantics where instead of just entering this loop and never exiting, we're sort of running these concurrently, and we're going to print a little bit from one, a little bit from the other. Yeah, that's the idea. And how can we do that? Well, if you have support for multi-threading and like splitting new threads and so on, you can just do this in the language. But if you don't, it turns out you can actually model this internally in a purely functional manner. So you don't need to extend your language, and you're still getting this kind of behavior with just a little bit of programming. So the idea here is you're still going to write a program that looks a bit like this, but you're not going to fully execute the first loop before you have the second one. So you will have concurrent threads. And to do that, I don't know if it's clear, but the intuition is that when you're defining this, you should basically run it for a little bit and then yield control over to whoever is coming after you, and then they get to do a little bit of work, then they need to hand over the control back to whoever is at the top level in charge of things, and then they will also stop, and you will keep alternating until no one has any work left to do. And of course, if you're going forever, then it will go on forever also. And the technique to do, well, there's a bunch of different techniques to do that, but the first idea is to use a different monad here. So here we have just pure IO, and so when we are declaring these to be sequential, they're really independent, and they're going to run in turn. But if we have something like the continuation monads, then this action, because the continuation will be passed to it, is also aware of what comes after it. And so once you're aware of what comes after you, you're able to do a little bit of work and then hand over to like the continuation. And then if the other action is also cooperative, it will hand it back, it can hand it back over to you eventually. So the first idea is to define the continuation monad, which is something like this. Let's define it like this. make count, run count, okay, now my buffer is really wide. This is hopefully still visible. So what is this doing? It's a computation that will return an R eventually, but the computation itself only computes an A. And so you can see that here, if you actually have an A, you can apply it to what comes next, and you will get the return type. But this is essentially the future. So if you know how to consume an A and return an R, I will give you an R. So implicitly there's an A in there. And we can indeed define the thing to be a monad. So cont R, where something, and here it's gonna be, I can never remember what it's like. It's like this. No, it cannot, unfortunately.
We can put a title.
Is it this? Yeah, that's this. Okay. But you get the idea, right? You want to turn A's into B's, you have a future turning B's into R's, so somehow you go find that future and you say, well, before you turn a B into R, turn the A into a B, and then into a R. And these are just like going under these lambdas, basically. And then we can do the applicative. The applicative one is a bit more interesting. So, as I said, if you have a value, you can return it immediately. What do you do? Well, you take your continuation, your future, and you apply it immediately. So I have this A. I know how to turn A to R, so I'm turning it to R. And then if you have two of these, it's a bit more annoying. So let's try it this way. Oh no, that's the function, that's the argument. And then what do we do? Well, if we know what to do once we have the result of applying the function to the arguments, we can, oh, I should do it like this. First, consider the function, and then once we have the value for the function, we consider the arguments, and once we have the arguments, we continue with whatever we're supposed to do. So instead of running the things sequentially in a sense, right, you're saying, I'm going to run this computation, and then the continuation, the thing I do after running this computation is just grab the function that I was given, and I need to return the R. So what do I do next? Well, I continue by exploring the computation for X, and once I know that I do get my hands on an X, I can keep going with f of X this time. That should be okay. It's not okay. There's a missing K. There we go. There's always a missing K in the computations. Monad. The monad is fairly similar, so you have some kind of A, and you can continue with an F. So what do? You grab the future, and then you're going to run MA to get the actual value out. And then once you've computed the next thing to do, you do it in the future you're envisioning at the start. I mean, these things, the definitions are, I mean, it's the only possible definitions based on the types. They are not very, they may be a bit confusing, but what matters is that once you have this monad thing, you can just write whatever you want in a fairly standard style. So let's see. Oh, okay, that's we can't really do that because we're computing pure values into. It's not a transformer, so let's not do that. So that's one part of the solution. Now you have access to the future of the computation. So from loopcat, if you think about it, right, this is taking the continuation, meaning what you're going to do once you're exiting loopcat, which means that you have access to loopfish. So now what you need to be able to do is to verify like bits of the computation to say, well, I'm going to compute all of bits, and then I will hand over to whatever the future is. Because at the moment, you can't really do much with these continuations. It's like really run the whole thing and then hand over. So that's where in this paper they introduce like this data type showing you what it means to have sort of a little bit of computation. So it's called an action, and it's over an arbitrary monads. And what can you do? Well, you can run an atomic action, and this thing, maybe I should write it GADT style. So what is this saying? This is saying I'm going to compute a little bit in M, and then I am to voluntarily suspend myself and return the rest of the action that I want to do. So this is this idea of not going all the way to a value and just doing a little bit. And this is called atom because when you actually run it, here you have no control whatsoever on M, so there's no way to split that M into sub-computations, meaning that action here will run fully until you reach the rest of the suspended, like the sliced computation. So in this concrete model, this is going to be an atomic action that cannot be interrupted by the evaluation of anything else. Then you have something like fork, where you have two actions, and that also creates an action. So the idea here is that the current action that you have is not only like computing something yourself, but you're actually going to split yourself into two sub-actions that then are interleaved and just computing concurrently. And finally, you have a stop message that says, okay, I'm done. You don't need to compute anything else. Yes?
So the fork is usually creating a new process. Is that the same concept, or it didn't sound like it?
Yeah, so if you look at Atom, for instance, right, usually you would be running an atomic operation, so it would be something like this. But you always have to explain how you're going to progress after the current behavior, right? So here we're showing not only are you executing these M's, you're going to return yourself. And so fork is the same, you're like forking off this thread, and then you continue as this one. And overall, that describes this entire computation. It's going to become clear maybe very shortly. And stop, you can see that stop is not storing a future action because you're just not doing anything anymore. So you can then define what it means to have concurrent actions like this. So conc A will be a thing that takes a value A and does a bunch of actions. So if from some A you can compute some more actions, then you can do actions. So that's actually cont action action M A. Oh, yep. Thank you. And then if we can define stuff like atom, which if you have a conc MA, will give you an action M. Is that the way it goes? Can't remember. Oh, no. Okay, that makes more sense. So now we can define operations that are all going to build actions into that concurrent monad of actions M. So the atom one, you want to run this computation here and then eventually do something with this. And so that goes something like make cons. You grab the future, and then what do you do? Something like this, maybe? No, it doesn't type check, or that doesn't exist. Let me see. So it needs to be an atom of is it? Yeah, you do need for this to be a functor. So what does this mean? Well, I want to run this action here. It will eventually return an A, and then I'm going to keep going concurrently. So what do I build? I build something in the continuation layer, taking the future atom here over C, says these actions are going to be run atomically. And then I'm going to go over that context of actions that are run atomically. I find the A, which is exactly what that continuation is waiting for. And that continuation is returning an action, which is exactly what you need to store in the sub computation here of atom. Okay, so then you can define, then you can define stop. So stop is giving you a concurrent action that does anything. And it's somewhat boring. So if you're stopping, you're not doing anything anymore, and you're ignoring the rest of the computation. And then we have fork, which is the more, well, maybe I should define this one. So there's action. So this one, I'm not sure how to describe the intuition for this one. So the yes, the idea here is that we're verifying the entire concurrent computation as an action. So as a description of these slices of work. And how do we do that? Well, we have our computation here. Oops. Okay. And if you remember the type, it's something that given given an A to action will return an action. So I just need to find the proper A to action argument to pass as a continuation. And because we want to verify the entire concurrent computation, we can just return maybe stop. So the idea is that we're going to do all of C and then stop eventually. So this
isn't that just right why the entirety of the concrete argument you're giving it?
So it is throwing away the return value A. Yeah. So you're going to execute all of the side effects, but you're going to throw away the final result, which is, I mean, that's the way it's cooked all during in this paper. Then we'll see how you can keep this, but it makes the setup a little bit more complicated. So I think that's where we needed to, oh no, fork. I said I wanted fork. So fork is something like this, where you have your concurrent action, and you're gonna build a new one. Yep.
Nothing. Do you need the monoconstraint action?
In here you don't. No, that's true. And in fork, In fork you do because you're using, oh no, you don't because you're using action. Okay. And what are we gonna do here? We're gonna do, let me remember. Yeah, okay, that makes sense. So as we were saying earlier, when you're forking a given thread, you're just saying, okay, this will be run like concurrently to me, and then I'm gonna continue like this. So then the intuition is that you're grabbing the future, which is I'm gonna continue like this, and we're gonna on one side do C, the thing you're saying should be forked off, and then on the other side you're going to continue as yourself, your own future. So this is why this representation still needs to mention both threads, but then the complement itself is only describing what happens to your future self, basically, and you're describing an entire computation here as part of the argument. So when you're saying fork, indeed, you're only going to mention the thing that goes away to compute something. And then as a side effect, it will return unit, but creates that thing that needs to run. And then the magic of it, of course, is that we want to be able to run these things. So in order to run these things, now that you have these descriptions, you're going to need to pick a scheduling strategy. So the example that's in the original paper is just run Robin. So because you'll be running all of these M actions, you need to be able to schedule them in a sense, so you need a monad constraint. And then you have a bunch of them that are currently active, and that's going to compute a value. Well, not really a value. We're more interested in just the side effect here. And how do you do this? Well, it's fairly clean. If the list is empty, you're done. You don't have anything to do. And otherwise, if you have a first action and some more actions waiting, well, it depends on what your action is. So if it's an atom, A, well, that's more like MA. We have it here at the top. It's some work you need to do, and then you will describe what the next step will be. So you do that work for a little bit, and then to ensure that there's actually an interleaving of everything happening, you're going to call within recursively, but this time you're going to put the future at the end, and so you're going to execute something else in turn. What's the other one? Your fork. So fork gives you two actions, and here the idea is the same. You're going to push them, but you've already taken your time, which was to fork, and then it's someone else's turn to do some work. Okay. And then finally you have stop, and there's no price for guessing what stop does. Stop just throws the current computation away. And so now I should be able to write something. Let's see. Maybe I need to write a lifter or something. Oh no, it was atom. That's fine. Okay, let's do that. Loop. So loop now is going to be in concurrent action with some IO returning whatever, and it's going to first print the string. Okay, so I need to put in my string. Yeah. Okay. And so now I can, well, I guess I should write one maybe. So one shouldn't be too surprising. When you have a single action, you can run it. by scheduling it alone. And then my name is now I or something, and it does run on the for loop cat loop fish.
So doesn't loop return just an IO?
I redefined it here.
No, but how does the right impression? How
Think about it, should take a conc and unit and then run action for the run is taking an action.
Yes.
Main is feeding it a conc IO.
Oh, yeah. Okay, we can do it like that. And it's action. Right. And so now if we run it, well, we can see that we are indeed interleaving everything because we have this idea of, we made the put string atomic, which means the entire put string runs, right? And then you're calling yourself recursively, but because of this fork here, the two executions are interleaved. So that was the setup as it is in this paper, and it's all fine and good, except that you're not returning the value A here. So run starts with the value of type A, and then throws it away. And that's kind of annoying. And of course, they're saying it's outside the scope of this paper and so on, but it turns out to be somewhat tricky to do. So let's see if I can perform the surgery here. So the idea stays the same. You want to do a continuation, whatever, blah, blah, blah. But then you're going to change your type of actions to actually mention the value they're computing ultimately, right? So now you have an action MA, and atom doesn't change because here you're doing a bunch of side effects, and eventually if you want to return MA, you still need an action MA under the hood. Fork, you're forking off the first threads, and then it goes and does some computation on its own. And then the second action is yourself, like you're preserving yourself, right? Yeah.
Could you make it so that you collect the results from both sides of the fork? So if you take an action made an action if you turn an action in and then duplicate.
So that's the next step. Yeah.
Sorry.
And stop. Well, stop this time. You don't want to actually get rid of the value. You want to keep it around. So when you're stopping, you actually need to return a value of type A. And this is almost similar, except that now there's something that needs to go in here. And the trick here is to, just like for the continuation monads, make it universally quantified. Because
Isn't that an extension?
no, because it's a type alias. Yeah. So why do we want to do that? Well, this is actually computing an A. We don't care what the future is. The whole point of this computation is the A. So the R is completely generic, but eventually when we call it, we'll make sure to feed in a future action that just immediately returns the value. So eventually the R will become the final A that we have, but at the start of the computation, we cannot predict what that future A will be. So then we can modify this. Does it still type check? Oh, that's right. Oh, no, there we go. That doesn't, yeah.
There's like something that doesn't like going
Right, so I think these primitives are still fine. Well, primitives, these defined operations are still fine. Okay, I need to sprinkle some stuff here. Yeah, so stop doesn't make sense. It's just pure. But let's get rid of stop. Let's get rid of stop. Here, when we want to verify an action, well, the future is just going to be returning that value, so that should be fine. And here we insisted that the first action returns unit because it's not doing anything. Wait, what? Yes. Hmm. Hmm. Hmm.
Yes, because the fork itself doesn't return value.
Right, but then we can build some more values later on, yes. And then the issue is when we start getting to here, because now you have a list of actions, and all of them might return something or may not return something, and eventually you want to compute the value of a given type. And it is really annoying. Maybe I'll go fetch the actual solution. So this is what I came up with, which is not the best, but let's see. Yeah, I should say this talk is an anti-dependently typed programming talk because the most obvious, at least to me, solution is to introduce this type. So I have a list of types, and for each one of them, well, they don't need to be types actually, they could be arbitrary A's. I have a predicate that's true. Okay. GDTs. No, no. Oh, yeah, okay. Is it actually? Oh, okay. I never use these things. I just write everything with it. Can you please? Ah, fuck. Okay. We're good. So this is how we have a type level list of arrays, and for each of them, P is true. And so then you can do something like this. I have some actions, and they all verify some kind of, they all return some kind of type, whatever the type is. And then if you want to compute the result, as I said, the most obvious solution here, if you're a dependency type programmer, is to insist that you have a function explaining how to turn a collection of all of these A's into all of the into a B. So run identity A. Okay. So now here I have a function, I have an empty list. I can just create pure on a nil. Why is it not happy?
Second one needs.
Or is it already complaining about the future? Yeah, okay. And here it's going to be a pain, you can see it, right? Because you're appending the A here at the end, which means you will get something in the form blah, 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 and then you need to explain how you're going to split the A here to pass it to the function and so on. So the solution, and this is actually already cleaner than the original definition in the paper, because instead of appending, what you're doing is really you're zipping around the list and looking at the next thing every time that you need to do. So it only makes sense to have like the actions you've seen already that are to the left of you. Then you're currently here and you're looking at the work you need to do. And eventually, when you reach the end of the work, you can just rewind everything. But rewinding is a process you can do, and where the types will just flow nicely into each other, whereas appending at the end of an org is horrible. So let's see if we have two empty things here, we can conclude. Or do I want to? Yeah, maybe I do. I can't remember. And when we are here, we've gone past. So this is annoying because it's the wrong way around, but F. And here the same. We've gone past A1 and A2. A2, A1. You're forced to think backwards, but you could write it another way. F2. And then when you have a value, your SVVs, FSV, cons AVs.
I think you need to use icons rather than the list ones.
For these ones here, that's true. Oh, yeah, in the pattern also.
And on the,
Yeah. So that's why I was complaining. And in here also. Okay.
Still comes up.
Well, I've left some holes, right? So we can look at these holes and they're not the. Oh, yeah. My bad. Mm-hmm. It's lovely, yeah. Boop, boop, boop. 64. Oh, yeah, this is expecting two things now. Okay. And now I have some holes, and I think it's clear they can, well, that they can be filled in. So here we have this first F where we can see we need to build this thing, but in context we this is terrible from a what? Oh, but there's an extra constraint knowing that this is equal to that and so on. I mean, the types are really not helpful with Haskell, but this is because of the dependent type. So I'll show you the solution instead. So because we're moving stuff from the right part of the things left to do to the left part, listing the things you've already seen, in the function transforming the results into the final result, you need to go the other way around. So now this thing has been shoved onto here, but you're just shoving it back this way. And then you call yourself recursively, and for a fork, it's exactly the same thing, except that now you're popping two things. Yep.
I just realized something I'm a little confused about.
Mm-hmm.
So you defined fork earlier.
Yep.
And I asked about this as well. And you used to define it so that all the branches return nothing. Except for one.
No, so the first one returns nothing. Yeah.
Yes. And so if you're repeatedly forking off stuff, then you only have one branch which can return.
Yeah, but you don't know which one. So when you have your big list of things, it's always the last one. Structure. I suppose it's true. Yeah.
Because if you're forking something off the first action there, then both sides are going to return. Yeah.
Yeah, I suppose it's true. You could have a different data type where everything is just assumed to be a unit until you reach the very last.
But that is this type,
Hmm?
isn't it? Sure it is.
Yeah, I think it would work, but
So then why we?
I don't know. That solution is unnatural to me because you're zipping around in the list of things.
I mean, it's clearly more general.
Yeah.
But what I'm saying is, for this particular data type that we have here, I'm not sure the generality is necessary. It would only be necessary if you do have a type in which both sides of the fork can return.
Yeah. Right. So, I mean, this is the solution that seemed natural to me because of the structure of the problem. but yeah, there's a simpler one indeed. Yeah, but basically we can keep going like this, and what you're doing is a lot of shuffling around of these values, popping them from the left to pass them to the right, and so on. And my argument is that this representation of, okay, we don't even have it anymore, of just having a list of the actions you're currently running, because we've lost the structure of the problem, which I guess is part of what you're saying, we, um, we have an overcomplication basically. And the structure of the problem is that we don't actually have a flat list of threads that are interleaved. We have a tree of threads, and whenever you're forking, then you're creating like two successors to yourself. And if we were to keep that structure around, we wouldn't need all of that complexity, which is the flattened version of this scheduling thing. And so then I'll just jump to 4, that's 4, I think, which is the last version in the cleaner version, I think. So we're just revisiting this thing. We still want to return the value we're computing. We still have our pure actions. We still have our like slight atomic layer of things we want to run. We still have our fork that discards whatever the first one is computing. But then we have this new thing called join, where you're not only running two threads concurrently, but then you might keep going with the results you're getting. And why do you have this? Because, well, just like with this atom thing, it's not enough to say, I'm going to compute an A at some point. You need to capture the entirety of the computation. So you do need that continuation here to be verified in the tree to tell you what happens after you join back. Unless, otherwise, the only thing you could do is join back and immediately return the pair of values. But I think in theory, you do want to potentially continue doing more stuff. And then the things are more or less the same, I think, except that now we have this concurrent operation where we can have two concurrent actions, one computing an A, another one computing a B, and we're going to return a pair of both A and B. And there's no surprise here, you're joining and you're capturing the entire future in the rest of the wayfied tree of actions. And then the solution to our problem, we're just zipping around these two lists to like popping values, pushing them, and so on, is to instead have a tree representing the structure of your computation. And now it's actually necessary because you have this join thing, meaning that at some point you might compute the pair of A and B coming from two subcomputations, but that doesn't mean you're finished. It means you're going to run something else afterwards. And so when you're writing your scheduler, you need to store at the node in the tree, basically, the thing that's going to keep going after you've run the two subtrees. So it's very natural here to have a tree construction. And it goes something like this. So you have a value where you've already done executing. You can have a leaf. A leaf is an isolated action that you'll eventually compute on A. Or you can have a node where you have two subtrees, each computing a value of a different type. And then what you do next once you're done with that action, with evaluating that subtree. And then instead of having two lists telling you where you are in the computation, you now have a stack describing where you are currently in that tree of executions. And so that's the idea more, right, is that you have your big tree of computations that you want to do, and you're somewhere in here. You're going to run your atomic computation, and then you're going to go back up to find the next one to run, the next one to run, etc., until you're all the way at the bottom right, which would be being at the end of your list, And in that case, you're going to rewind and go back to the start.
Sorry, the screen just went off.
And so now that we have types all over the stack, we can actually give it a type also, and it will be fairly clean. So if we have the ends of the stack, so all the way to the top actually, then the type of the inner action that's going to be running and the return value will be exactly the same because now the stack is empty, so ready to return. Otherwise, we might be going to the left of a given node, in which case we have always that further computation that's stored in the nodes. We have the stack for the left that we're going into, and then we have an action for the right subtree. Okay, and that takes us from, let's see, so I can go from A, given a B to C, and should I actually try to make sense of this? Yes, so if I know how to compute on A, then eventually I'll be able to call this function, and I know how to continue from the C to return, and so that gives me a return. And the B here is if I have a value eventually also. And I can also go to the right of a subtree, and that's a similar setup. So if on the outside I know how to compute a B, internally I know how to compute an A, and when I have both of these, I'll continue with a C, then continuing with a C to return gives me the ability to compute a return on the way out. But it's hopefully clear with the definition of Robin. So let's see. If I have a value, then I'm going to unwind, which we'll look at later. But basically, my computation is done, so I'm going to go look for the next bit of computation in the stack that I have left. If I have a leaf, which is these actions that we were looking at earlier, then I look at it. If it's a pure value already, then I know I can unwind. If it's an atom, then I'm going to run a little bit of that computation and then go look for the next thing to run in my stack. So next and unwind are different because unwind is taking a value, but next is taking an action already. There's some more work to do. If I'm forking, well, I'm going to create these two sub-computations and I'm going to say, okay, schedule them at some point in the future. I'm going to look for the next thing to do. And finally, in the join, I'm doing exactly the same thing, except that now the value computing the future work is actually interesting. It's this J thing. And then, yeah.
So fork here is redundant. So
Yeah. Well, there could be an optimization, meaning that you're not necessarily waiting for things to run and so on. But, and then if I have so that was for the leaves. If I have a single action I'm currently considering, and if I have a node in the tree, well, as I said, we're going to go left to right through the tree to execute the action. So we're exactly going left, looking at the action on the left, but remembering the work that is left to do on the right-hand side. And so then unwind and next are fairly similar. Unwind, if you reach the top, you have a value, you're ready to return it. If you are somewhere on the left, then if the value of the right subtree is already known, you can compute what you will do next and schedule it for at some point in the future. If it's not a value yet, then you do want to evaluate it. You do want to run a little bit of that action. And if you're already on the right-hand side of something in the tree, well, again, okay, if you already have a value, you're happy to make it go. But otherwise, you're going to build that node and go look for something that's to the right of you because you're always trying to move to the right. That avoids staying in a loop locally and never exploring the rest of the subtree. So when you're on the left of the node, you're always going to go on its right. But when you're already on the right of the node, the next thing to your right will be one level up. So you unwind some more, or call next here. And this is exactly what next is doing, right? If you're on the left, you can run the right thing. And if you're on the right, you have to go one level up and then further to the right to you. And then because all of these types are lining up, you'll notice that you don't need like these dependency type things anymore. You can just run a given action on a given stack. Yes. And one is, again, exactly the same thing. You verify your computation and run it on the empty stack. And then we can have an example. So I have Fibonacci as an example. Click. And that's a good example because this time we're actually using the results computed by the two concurrent actions. So if we reach a base case, we just announce we found a base case and we return the value. Otherwise, we create some fresh names, whatever, for the subthreads. We're announcing some things we're doing, but here we're running concurrently the n-1 and n-2 computations, getting the results back, and combining them. And so if I run, oh, is this, okay, it's weird. If I run it on 5, then I'm getting a bunch of outputs showing that the evaluation is indeed interleaved, and because we have this new join construct, we're able to compute the value at the end. Yeah, so that was the idea. Yeah.
If I understand correctly, you were doing some kind of like work schedule.
Yeah.
Is this like a standard scheduling algorithm that already exists you're implementing, or is this a new contribution?
Yeah, so that's the round robin
Yes.
scheduling.
It's like if gets equal
Yeah.
and your algorithm is just a round robin? Or?
Yeah. Yeah, so
Well, there's a particular structure of what's blocked or not. We can't schedule certain things until other things are finished.
Yeah, something that's blocked.
yeah, because you have join points. Yeah. So
There might be cases where you have nested joins, then you might be losing some concurrency because the thing outside the join might not execute something. So you have 3 processes.
yeah.
You have to run 2 parallel in the join, and the third joins. But I think only the first 2 will concurrently execute. And they finish, and then the others up.
No, that's fine. So if you use fork, the future action is just a pure thing, right? Where is it? Fork. Do I still have it here? Always in the semantics. So if you're using fork, you're not actually waiting on anything in the future, right? So because of the way you represent it, which was actually, yeah, that was the good thing. So you have the first action you're forking and then the entire future. So if you have more forks, there will just be nested forks here.
You get rid of the fork constructor in place of the join. Follow up is so we have 2 units.
Well, so here we are waiting on both of these before we run the continuation.
Isn't that how you implement it?
So yeah, in the semantics, okay, so you could define fork in terms of these, but then what's the blah, 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 blah. is it, yeah, it's something like this, right? Make const k. So you want to run the entire k, so it's going to be action c, k this, and then when you get a and b, you return kb.
No, you're returning pure.
Mm. Oh yeah, you've run k already. Yeah. Yeah, so you could do this. Yeah.
Is that on the same semantics?
Yeah, because so here you have a sharded tree, right? So if you have more forks inside, you will just have nested joins. And when you're evaluating a join, you are evaluating both of the subtrees, and it's only the future computation that's blocked on waiting for both of these values. Um, so that's fine.
The only thing that's funny there is that if k of void takes forever, something might take long to run a lot.
And if, so you might expect a fork. If you, from the main thread, you fork process which loops forever,
Yeah.
even production. The main program with, within the previous one on the list, you could have semantics where the main thread finishes and the whole program finishes.
Right. I mean that, yeah, it's not the semantics that you have, but you could,
but we
yeah.
should have semantics where the whole program doesn't finish until all of the threads finish.
Yeah.
I think in physics threads, and the main program finishes all the other ones.
Yeah, because you have more like a wait, explicit like waiting instructions or something. Yeah.
You can wait for them, you might have a background thread that always wants to do is caching.
But then you have a syntax with binding, sort of.
Well, those are pretty bad because then they don't get peanut.
Yep.
Where do you put this investigation? What kind of problem are you trying to solve?
Well, so I was reading this paper first, and then I tried to figure out how to add join points, and so that was the main idea, and in a clean way, yeah.
Do you see it like eating into some dimension of these concurrency DB?
Not necessarily, but yeah, it is for 316 mostly.
Yes.
Yep.
Last year I was trying to use this grammar to implement an active language.
Okay.
After the time powers active language sequence, and I just use the basic stuff to implement some other stuff. Maybe we can talk later.
Sure. Yep.
The other thing that always strikes me when I see stuff like this is when you have processes that go to sleep, there's an opportunity to have them wake up after the world's changed. But whereas here they're waking up exactly as they were. It's also kind of interesting to see joins are one thing, but it's also quite fun to say, I'm not going to wait for these two things to be ready. I'm going to carry on with placeholders for their outputs.
Right.
I'm really locked. This is I guess what I'm trying to say is that I wouldn't want, for example, to implement a concurrent type checker like plus. There's some missing machinery.
Yeah, so I mean, there's a lot of power because of the continuation monad that automatically verifies your future and so on, but also you're sort of limited, right? When you're saying, I'm getting these two values and I'm going to do some further work because it's all implicit in that continuation. There's no way for you to say whether it's independent from these values yet or not. So, yeah, I'm not sure how to handle that in a lightweight way, like in the setup. And the nice thing compared to the abstract machine in Typos is that everything is typed here. And, you know that you're going to get a result. And, I was thinking also adding mailboxes and messages because that's something we've been doing in Typos. In the paper, they just explained the fact that you can have any arbitrary monads as your underlying monads in the concurrency one. It's a monad transformer, right? And so in particular, you can use IO and then have n vars in there, which is fair enough, but it feels a bit like cheating. Suddenly you're escaping that ad hoc concurrency monads, wherever it is defined here.
If you could return futures instead of actual values, more flexibility.
Well, not really, because here we're still.
Well, I mean, maybe that's the actual one. So, in the actual example, you've got two subcalls. So
Yeah.
you can use conc, your two subcalls. If you wanted three, then you might think you could have the next line say fork another thing to do the third one.
Yeah.
But what you have to do is put it all in one line. And unless the conc clear to get three parallel things. Because otherwise, if you do one after that, it will run those two parallel, then run the other one.
Well, even if you put them all on a single line, they're still.
I mean, if you do conc, job one, conc, job two, job three.
Yes.
Then it will,
Okay, the job two, yeah, job two, job three will super quickly fork off. Okay, yeah, yeah.
that's why we wrote fork now, it's very different semantics.
I mean, yeah, no, fork is fine. Fork is fine because you're capturing the entire future in the second one. Yeah.
No. That just matter of fact, like the way that you're always like branching to the right, just make sure that you're doing everything.
Fork can't change that.
Fork can. So,
Because if I pass their value from C to K, so already passed.
well, it's returning this one, which is the value computed by this thing. Well, which is arbitrary. It's polymorphic, right? K is for R, action R. So you're getting the empty from here, which is passed to you immediately. But whatever the follow-up computes is what you get out. So
Yeah, but you have fork something.
I know. No. Yeah, so here I don't know, you need another thing that has some essentially mailboxes, right? And then you could compute the continuation immediately by passing in the references to where that thing is going to go. And then you can have an operation that tries to read from them and blocks if the messages are not available yet. Which you can probably just have a global environment for these things, right? So
Dynamic allocating. It's like in terms of binding. Points of the tree which generates a name.
yeah, well, you need yeah, okay, then you need your scopes and presheaves and whatever. Yeah. because yeah, it's only increasing, right?
Another comment is that there's also some really nice mathematical structure inside this, but because it's Haskell, we don't actually get to see it. For example, like the action monad, it has universal property. And also, I feel like you use the co-density at some point, right? That's the one when you put it for all.
Mm.
Yeah. And also, I was wondering these, like when you return the type of fork, it's A, B, but really it should be an unordered there. You don't want to force in the types.
Mm.
Some of these things could be like for truly different actions.
Look, you were saying you're getting both back.
Yeah, it's a join points, right? So you are getting both. Your stock until you're getting both answers back.
But what if I want to say that forking P and Q is the same as forking Q? So really these actions should be quoted by symmetries.
Yeah, I mean it is modular. Yeah, isos the results.
Modular by simulation.
Yeah.
Yeah, that's true.
So I mean, you could use this to build the real semantics of like CCS and stuff.
Mm.
To actually impose the equations.
Right.
So if we have dependent types, quotients, things.
Clemens asked the question, how would you verify the properties of the concurrent behavior? Which I guess you would use Haskell to do that.
Well, yeah, I guess. I mean, what property do you want to verify to begin with?
I'm afraid Clemens is long gone.
Yeah.
I mean, yeah.
I mean, so the thing is, I did think about like doing it in Acta and then proving some properties and so on, because that would be a good reset for one. But the problem is that this is going to be horrible. You're having some kind of full monad. I mean, there's more things thrown in, but over an arbitrary m. And you can do that in independent type programming. So we could use now we have polarity annotations and like that, but we never see them in lectures, so that feels like a bit too much work, maybe. Or we could just use a signature of like some kind of effect, and then work more syntactically, but that feels also wrong.
That is a commutative one. Then the behavior should be the same as just running it with code spreadsheet.
Mm. Do we have a lot of commutative ones?
Maybe writer or
And also, this is Robin Milner's synchronization trees.
Okay.
So yeah, so synchronization trees are truly abstract biseparation,
Okay, nice.
but to actually implement it in a program language, we need
Yeah.
maybe using the identity model is not that useless, because if you imagine that would say if you generally run the joins in parallel,
Mm-hmm.
it would say that the sequential behavior should be equal to the parallel.
Okay. Yeah.
But you would allow one them.
Mm.
So next week,
Oof.
Yes. Yes, Ren will be presenting next week. I don't have a topic yet. We will do soon, and I will upload because I've been recording this via OBS, so I will upload this recording to YouTube instead of the live stream.